back in 2010, when I was a sophomore in high school, I saw a kid playing with the Rubik's Cube and thought to myself, that would be pretty cool if I could learn how to solve one of those myself. So that summer, I watched a bunch of YouTube videos and tutorials and taught myself how to solve it. By the time school started back, I was able to solve the cube in less than a minute. After much intense practicing over the course of many months, I was able to solve the cube on an average of about 20 seconds. But in 2016, I retired from speed cubing entirely and decided to spend more time on practical skills, such as computer programming. Around this time is when I started working on a project that I called Twisty Puzzle Masters. This tool showed the user how to solve their scrambled cube step by step by allowing them to recreate the two-dimensional representation of their scramble on the user interface and pressing a button for it to generate the solution. However, I completely lost interest in this project after a few months and moved on to other things. But finally, I revisited this project and gave it the much needed TLC that it deserved. The tedious 2D cube interface was replaced with a new method that uses color recognition by allowing the user to use their phone's camera to take a picture of each side of their scrambled cube to create a virtual representation of it. The app then uses my logic and data structures to generate all of the steps required to solve the recorded scramble. The purpose of this video is to showcase the development journey of how I got this to work. Let's jump right into it. The first thing that we need to get the app to work is a data structure to model the cube and its physical behavior and properties. The name that I chose for my data structure is the Rubik's Cube structure. There are four main actions that you can perform on a physical cube that the data structure and code must also be able to mimic. These actions are rotating a specific layer of the cube, identifying a specific location of a desired piece, identifying what piece is already at a desired location, and finally, executing a given algorithm. Let's take a look at the rotate method. The rotate method does a few things. Basically, it updates the state of the layer that you're going to rotate. In this case, this is the up layer and this is a clockwise rotation. So what that does is it swaps the side sticker colors with each other based on where you're rotating. Then it also updates the state of the top sticker colors in the data structure. So in this case, the side here on the right is the blue side, and if you do a clockwise rotation of the up layer, that right border becomes the front border. The next thing that we need to implement is a method that can identify what piece is at a specific location. To do this, I created a method called getCubie@location. A cubie is just a small piece on the cube, so this white, blue, and red piece is known as a cubie. Say that we want to identify the piece that is at the front right up location. Well, we would look at the front side, which is white, the right side, which is blue, then the up side, which is orange. That is this piece right here. So if we were to pass front right up to the method getCubie@location, it would return white, blue, and orange. So the next method that we're going to cover is the find location of cubie method. The purpose of this method is to do just that. We're going to find the exact location of any piece that you're searching for by color. So for example, if we were to look for the blue and white piece, the location of that one is exactly the front and up layer. If you were to pass blue and white to that method, it would return up and front. And finally, we need a method that shows the data structure how to execute an algorithm. An algorithm is just a list of steps. This is an up rotation, this is a down rotation, this is a left, this is a right, this is a front, and this is a back. And this is the code that shows the data structure how to execute any algorithm. It took me about 100 hours to develop this entire project. That time was spread across 3.5 months, and I only showed 4 of the methods associated with the Rubik's Cube data structure in this video. However, across all of the different classes and files, I ended up having to write thousands of lines of code to get the app to successfully solve any scrambled 3x3 Rubik's Cube. Implementing each one of these methods took many hours of debugging, testing, and verification. One of the most challenging aspects of this project was trying to rewrite parts of my code to interface with the new OpenCV color recognition code. The part of my app that lets you scan the cube by taking a picture of each side was written by Yusuke Uchida. This is his GitHub page. After downloading his code and analyzing it, I quickly realized that I would have to significantly rewrite large parts of my app to get it to work with his code. The main issue that I was faced with was the way that he represents the Rubik's Cube is completely different than the way that I represent it in my code. He chose to use a single 54 character string that's used to represent the 54 stickers on the cube, whereas I represent the cube using 6 layers to represent the 6 sides. Personally, I think that his solution was a genius idea. However, deciphering the format of his string to figure out how exactly it's used to model the cube took me forever. It was like trying to decipher the Rosetta Stone with very little context. I was pretty intimidated by the challenge when I was first faced with it. I didn't even know where to start, but after much debugging and hand tracing his code, I finally figured it out. This is the map that I created to help me trace how his string works. Another very challenging thing that I had to figure out while making this project was how to represent the 119 CFOP algorithm. CFOP is the method that I use to solve the Rubik's Cube, and it stands for cross, first 2 layers, orientation of last layer, and permutation of last layer. These are all of the 41 algorithms for how to solve the first 2 layers of the cube. The challenge was, how do I represent each of these in code so that the data structure can recognize them and properly execute the correct one under the right condition? My solution was to use JSON. I designed a custom format for each type of algorithm. This is the format that I created for the F2L algorithms. After coming up with this format, I then had to manually map each F2L case from human readable images to the new format. These are all of the 41 cases represented in JSON. That's just for the first step of solving the cube. I had to do this also for the OLL and PLL steps as well. Coming up with the different JSON formats that could be used to represent each of these cases took me at least a week to figure out. I'm sure there was probably a much better solution that I could have used for this, but this one got the job done. All of the source code for this project can be found on my GitHub page, Downs990, and the repository called Twisty Puzzle Masters. Also, I created a notes document to try to help explain the solution code in better detail. That document is called Twisty Puzzle 2.0 Project Notes, and it can be found in the notes directory of the project repository. I started working on this project back in college, but I only worked on it for a few weeks. Around early 2017, I got busy with other projects and left this one unfinished. It wasn't until 6 years later, in 2023, that I recently went back and finally finished it. This project taught me that no matter how old a project is, it's never too late to revisit it and breathe new life into it, because it just might become one of the most amazing things that you've ever created.